Hello, Mr. Betts here. I'm going to take a look at a couple examples where we're finding critical values of a function. And I want to remind you of the theorem that says that if a function has an extreme value at a point, it has to be at a critical value. So this is going to be kind of a beginning step to finding the critical value, or I'm sorry, finding the extreme values of a function. So we're given a function. We want to find critical values. Remember, critical value is where the derivative is either equal to 0 or the derivative is undefined. So we'll say not differentiable. So what we're going to do is we're going to start by taking the derivative, and then we're going to take that derivative and see where it's equal to 0, see where we can't define it, and then make sure that they are critical values, and then we're done. So derivative here is going to be 6x squared plus 6x minus 36. We can just write equals 0. You do want to make sure you write the equals 0 to show that we're setting that equal to 0 for this part of it. I do want to point out that if the derivative is 6x squared plus 6x minus 36, it's always differentiable. There's no x value that we can't plug in here to get a value. So the derivative always exists. So really the only critical values we'll get is where it's equal to 0. To solve this, I am going to factor out a 6. And then I will factor the polynomial that's left. Looks like it's going to be x plus 3, x minus 2. And then solving that, we get x equals negative 3 or x equals positive 2. Now, the last thing we always want to do when we're finding critical values is make sure these are actual values on the function. And we can plug in negative 3 and we can plug in 2 into the function. I don't know what those values are, but I'm not asked to find them here. We just want critical values, so this is good enough. I will say that if the problem had said, instead of critical values, it said critical points. Remember, a point is an xy coordinate. So we would want to plug these x coordinates in to the function to get the y coordinates, and then give those ordered pairs as our answers. Same problem or same question, different function, so different problem, I guess. So again, critical values, we're looking for where the derivative is equal to 0 or the derivative is undefined. So we're going to start by taking the derivative. This particular function is a product. So we have x to the 4th as a function, e to the x is a function. So derivative of the first is 4x cubed times the second plus the first times the derivative of the second, and derivative of e to the x is e to the x. Then we're going to set that equal to 0. I do want to point out again that we can plug in any x value we want into the derivative, and it's going to be defined there. So we don't have any troubles with the derivative not being defined, so the function not being differentiable. So all our critical values we're going to get from where the derivative equals 0. This time I'm going to factor out the e to the x, but I'm also going to factor out an x cubed. So we factor out x cubed, and we got e to the x, and then what's going to be left over is going to be 4 plus x, and that's equal to 0. So we're going to get critical values. All right, CV at x equals, if we set x cubed equal to 0, we get a critical value at 0. Technically, we get 3 critical values at 0, but they're all at 0, so we're just going to list that once. If e to the x is 0, well, there's no x value that gives us 0 for e to the x, so that doesn't work unless it's, well, no, that wouldn't work either. And then if we set the 4 plus x equal to 0, we're going to get negative 4. So we get critical values at x equals 0 and x equals negative 4.